Welcome to this lecture. In the last lecture, we were discussing about the equivalence class test cases. We had identified when a function or a unit takes a single parameter, we can examine the input value and then identify the set of equivalence classes. One is the valid set of value, another is invalid set of value, and then for each of the valid and invalid we can identify different sets of equivalence classes. But then we are discussing about multi-parameter functions, because it is quite common that a function takes more than one parameter, and in that case how do we identify the equivalence class? One way is that we can identify equivalence classes corresponding to each of the parameters here, and then for defining the test case, one way is that we define the test cases such that every point here in this set of equivalence classes and a point, a representative from this set of equivalence classes and a representative from this set of equivalent classes is considered. The other way is that we have a exhaustive combination of the points from these three equivalence classes. So, these are two different strategies to define the equivalence class test cases. We will just look at it further, we will develop this idea further in our discussion today. But before that, we must be aware that not only is that a function like post grade can take the roll number, course number and grade. So, the teacher assigns a grade for a specific course to a student identified by some roll number. There are three parameters for this function post grade, but also there can be some global variables. For example, normalization factor. Let us say we have a policy of normalizing the grades, and we multiply the grade with a normalization factor. Now, we can think of this as an additional factor which influences the outcome here, and therefore, we can form equivalence class not only corresponding to the three input parameters, but also corresponding to the global variable. Just extension of our discussion of multi-parameter function is that a global variable accessed by a function is similar to a parameter to the function, and therefore, we must identify the equivalence classes corresponding to that parameter, and then we combine the points from these different equivalence class. Let us do some more practice. Let us say we have a function which takes two parameters. One is a integer between minus 99 to plus 99. Let me just write the function name as, let us say, some f. Name of the function is f, takes two parameters. One is a integer parameter and it defines a range between minus 99 and 99. The first parameter takes any value, the valid set of values are the minus 99 to plus 99, and the second parameter is a phone number. The phone number is defined by an area code which is between 11 to 999, and then there is a actual phone number, the area code and the phone number, and the phone number is, let us say, 6 digit. So, the second parameter is a phone number. which is again a integer, but then the first 2 or 3 digits they correspond to the area code and the suffix 6 digits correspond to the phone number. Now, how do we identify the equivalence classes for this? Of course, the first thing is that we identify the valid set of equivalence classes and invalid set of equivalence classes. For the first parameter, the valid set of equivalences are between any number between minus 99 to plus 99, and then there are two invalid equivalence classes, one is less than minus 99 and another is greater than 99. But what about the second parameter? The second parameter again we have a valid equivalence class where we have a 6 digit integer suffix and the first the prefix, that is the area code, is between 11 and 999, and the invalid set of equivalence may arise because the area code is wrong or maybe the suffix is wrong. If we write down our idea, we will have this. One is that we have for the first parameter is a range, and then we have one equivalence class which is one is the valid equivalence class, which is any value within the range. Another is the invalid equivalence class, which is less than minus 99. One more invalid class is greater than 99, and then we can have other equivalence classes as well. For example, malformed numbers, some are characters and so on, non-numeric strings, empty value, etc. These are the different invalid equivalence classes. Similarly, for the second parameter, we have a valid equivalence class where the area code is between 11 to 999 and the phone number is between 0000 to 9999. Now, the equivalence invalid equivalence classes are, one is the invalid format, we do not have the area code and the phone number, or we might have the area code which is less than 11 or greater than 999. These are two different equivalence classes, invalid equivalence classes. Area code with non-numeric characters, phone number which is 7 digits, phone number which is character, and so on. So, we will have many invalid equivalence classes and one valid equivalence class for each of these. And once we identify the equivalence classes for the two parameters, then we combine representative values from these two equivalence classes corresponding to the two parameters to define our test cases. At the simplest, we will discuss about the weak equivalence class testing, where let us say we have two parameters, age and education. Let us say for the age, we identify two equivalence classes. One is age greater than 30 and the second is the age greater between 20 to 30. These are the two equivalence classes. Similarly, for the second parameter education, let us say we identify three equivalence classes: school, UG and PG. This is the education. Depending on the years of education, we identify whether it is a school education, UG education or a PG education. Now, how do we combine these two values from these two parameters to form the test cases? One way which is called as the weak equivalence class testing, is that we see every representative from every equivalence class is represented in the test case. So, we see that every equivalence class from the first parameter is covered, and similarly every representative of the equivalence classes of the second parameter are also covered. So, if we have let us say n equivalence classes for the first parameter and let us say m equivalence classes of the second parameter, then how many test cases we need to be able to do a weak equivalence class testing for this function. Can think over it, but then let me just tell you that we will just take maximum of n and m, and that will form the number of test cases required to carry out weak equivalence class testing, which will have every representative from every equivalence class to be part of a test case. The other way we can combine the representative values from different equivalence classes is called as the strong equivalence class testing. Here every value of one equivalence class of one parameter is combined with every equivalence class representative of every equivalence class of the other parameter. So, for the first parameter here of age, we have one representative from school, UG and PG. Similarly, for the second equivalence class of the age, we again combine with the three equivalence classes of the second parameter, which is the year of education. Or in other words, for every value of the second parameter, we combine with every other value of the first parameter, and this is called a strong equivalence class testing. So, the question here is that how many test cases will be needed if we have two parameters and let us say we have m equivalence classes for the first parameter and n equivalence classes for the second parameter. Since for every equivalence class here we must combine with all equivalence classes of the second parameter, we need m into n test cases. Based on the equivalence classes, we can also combine them in another way, which is called a strong robust equivalence class testing. If you look at the two types of testing we considered earlier, we did not consider the invalid set of equivalence classes, we just considered the valid equivalence classes. But if we consider the invalid set of equivalence classes also, then we call it as a robust testing. The idea is simple, just a small extension of the strong equivalence class testing. Here we consider the invalid values as well, and this forms our set of test cases. If the valid plus invalid, we have m equivalence classes for first parameter, n for the second parameter. So, these are the sum of the valid equivalence classes and invalid equivalence classes, then the number of test cases needed for equivalence class testing will be m into n. Let us see, let us try to solve some examples. Let us say for a bank application, we have a function. The name of the function is compute interest and the parameter is days, which is a integer, and the function description is that it should compute 3% interest for deposits less than 15 days, 4% for deposit between 15 days to 180 days, 6% for 180 days up to 1 year, and 7% for between 1 to 3 year, and 8% for 3 years and above. So, what will be the equivalence classes here? This is a rather straightforward example. We have just one parameter and we examine the output, and each of these correspond to a scenario, and then we consider one equivalence class corresponding deposit between 0 to 15 days, 15 to 180 days, and so on, and the invalid set of inputs, which is an invalid day, negative day, and so on. Now, let us try slightly more complex problem, where we have the compute interest, but then it takes two parameters, principal amount deposited and the days for which the deposit is made. And the function description says that if the deposit amount, that is the principal, is more than 1 lakh, then the rate of interest is 7%, 8%, 9%, but if the deposit is less than 1 lakh, then it is 6%, 7%, 8%. So, we see here that for the two parameters we have two equivalence classes, one is more than 1 lakh, less than 1 lakh, and the days is 1 year, 3 year, and more than 3 years. So, we can have either a weak equivalence class testing or a strong equivalence class testing as required. This is another problem. Let us say we have a function called a substring, takes two parameters s 1 and s 2. S 1 is a string whose length is between 20 is up to 20 characters, and S 2 is a string whose length is less than 5 characters, and the function checks whether the second string is a substring of the first string. Again, we can form two equivalence class hierarchy. One is based on the string which is less than invalid set is more than 20, or it can be a control character and so on, and then the valid set of strings for S 1, valid and invalid set of S 2, and then we would have another equivalence class hierarchy, which is whether it is a substring of this or not a substring of this. If we represent here the data, input data for S 1, we can have invalid and a valid set of equivalence class. Similarly, for S 2, we will have valid and invalid, and also by looking at the S 1 and S 2, for valid S 1 and S 2, we can have another hierarchy whether it is a substring or not a substring. Now, let us start discussing about another type of black box testing called as special value testing. In the equivalence class testing, we divided the input data domain into equivalence classes such that every point belonging to one equivalence class resulted in similar behavior. But here there are some values which are suspect. The tester has reasons to believe that execution of the program with certain specific values may expose bugs. There are two types of risky values that a tester can identify. One is called as the general risk. The general risk, this is identified by examining the equivalence classes, and the boundary values of the equivalence classes in general are suspect. But then there are special values which are of risk, which may not be boundary. For example, the tester might think that okay, for this function which takes a year and produces the number of days in the year, is the leap year considered by the programmer or not. So, this the tester, by looking at the functionality, he guesses some values which might be prone to error, and those are called as the special risk values. In addition to equivalence class testing, we need to do special value testing, and one type of special value testing is the general risk. An example is the boundary value testing, and also the special risk data values should be used to define test cases. Now, let us look at the boundary value analysis. This is a general value, general risk. Whenever we identify equivalence classes, the programmers are very prone to commit errors at the boundary of the equivalence classes. Here there is one valid set of equivalence class, valid set of values which constitute an equivalence class, one invalid set of values constituting an invalid equivalence class, and another invalid equivalence class. The programmers are likely to commit errors at the boundary here. For example, here whether one is included as in the valid or invalid, they might not have taken care of that sufficiently well, and therefore, mistakes may occur here at the boundaries, and therefore, we must include the data values at the boundary as test cases, and those are called as the boundary value test cases. The main reason here is that programmers sometimes confuse, and instead of less, they might use a less than equal to symbol and so on. And that is the reason we need to select test cases at the boundaries of different equivalence classes, if boundaries exist. We had seen that if it is a set, input domain is a set of values, then there is no boundary. But if it is a range of values, then there are boundaries between different equivalence classes. Now, let us see, if we have input is a range, it is a range and the boundaries are A and B, then we need to select not only A, but we need to select one that is beyond A, just to check whether the programmer has made a mistake, and even the one which is should be an invalid or a different equivalence class is also considered as part of this equivalence class. Similarly, we might take a value that is just inside, and similarly for B, one on B, another slightly inside and another just outside. So, if the range is defined as any value between -3 to 10, we can take -3, we can take 10, these are the two boundaries, one slightly away outside the boundary which is -2, 11 and one which is just inside the boundary. This actually can be the equivalence class test. So, we need to define 5 values for a range. Similarly, if the input is a range, let us say 3 to 102, we will define one at the boundary 3, one is 102 included the boundary in the test case, one beyond the boundary on the lower side which is -1, another beyond the boundary on the higher side which is 200 and one in between which is 5. Let us see for some specific examples how do we define the boundary value test cases. Let us say for some problem where the function is based on the age, it recommends whether can be hired or not hired, checks if the age is between 0 to 16, it displays do not hire. If it is between 16 to 18, displays can hire on part time basis. If it is between 18 to 55, displays may hire full time, and between 55 to 99 do not hire. So, there are 4 equivalence classes here corresponding to these 4 different scenarios, and the boundaries are at 16, 18 and 55. But then we must realize that this description of the function itself is a bit problematic, because is 16 considered as do not hire or is it may hire on part time basis. Similarly, if it is exactly 18, what should be the output? Similarly, 55. So, even when describing the problem, we can commit mistake at the boundary as exemplified here, that the boundary values we have not taken care sufficiently. It is the specification of the problem itself is defective and not clearly identified the boundary should belong to which equivalence class, and of course, the same thing will get reflected in the program, and therefore, boundary value testing is very important. We will stop here and we will continue in the next class. Thank you.